We are working with section 3.4, exponents and logarithms, and with this application of functions involving exponential expressions. So very often we have exponential growth, and then we have a changeover where maybe the rate of change increases, or the rate of change increases rapidly, and then it gets to a point, there's what they call a point of inflection, where the rate of change decreases. And so you have a curve that's very much like an exponential function. It gets to that point and then it levels off, and then the cases decrease, and it ends up having what's kind of like a carrying capacity for the virus, if you will. It's only going to reach so far, and then people become immune to the disease. But here we have a function for this. The spread of the flu in a certain school is modeled by this equation, where P of t is the total number of students infected t days after the flu first started to spread. Estimate the initial number of students infected with this flu, and then how fast is the flu spreading after 4 days. So one of the things that we can do, since I am taking derivatives, I can change what this looks like and just make it 200 times the quantity to the negative first power. But I'll answer question A first before we get into the derivative. So I'll say that P of 0, we want to know initially how many P of 0 is then equal to 200. And that would be over 1 plus e to the 5 minus 0 power. So we get 200, and that's over 1 plus e to the 5th power, 1 plus e to the 5th power, the equal sign there. And so that turns out to be approximately equal to 1.3385, something, and so that's 1.339. I rounded it to 4, and there's 5, because generally what we do is we round it to 3 digits with the AP standards being 3 digits. So we're looking here at the 5, so we would say approximately 1.339. Okay. All right, so where are we headed now? Okay, part B, it says, how fast is the flu spreading after 4 days? So for part B, and the units on that, we would say that there are students. The units are students. 1.339 students, right? Total number of students. So a little more than 1. I mean, generally it's 1. All you need is 1. So for the second part of this, we want dp dt, or p prime of t. Remember, you have to put units in the end, so sometimes it's always a good reminder with Leibniz notation. So we have 200 times, we have the derivative with respect to time of this. I'm going to rewrite this so as 200, and then it's 1 plus e to the 5 minus t power to the negative first power. Okay, so I'm going to take the derivative of that, 1 plus e to the 5t power, and then to the negative 5 minus t. Oops. Okay. 5 minus t power to the negative first power. So we're just going to use chain rule with this. So this is then 200, and then it's times negative 1, times then 1 plus e to the 5 minus t power, and then that would all be to the negative 2 power. Oh, wait, hold it. Wrong. This would be to the negative 2 power. And then I'd have the parenthesis on it, and then taking the derivative then of e to the 5 minus t, which would be e to the 5 minus t, and then we'd have to multiply that by negative 1 as well. Okay, so then with a little simplifying here, we have 2 negatives, which would make that a positive. This is all a product, if you will. So I can make the negatives here, here. And then as I simplify this, I've got 200, and distributing the 1 is not, so I have a 1 e to the, so I'm going to end up with 200 e times e to the 5 minus t power in the numerator. And this expression is going to go to the denominator then, so that's going to be over, I'm going to put it like this, over the quantity 1 plus e to the 5 minus t squared then in the denominator. And what we want to do, we want to take this is our dp/dt, and since I'm running out of room, what I'm going to do is I'm going to then say this, I'm going to then evaluate this at t is equal to 4. We want to know how fast is the flu spreading when t is equal to 4. Now, I'm going to let you put that in your calculator and get an approximate answer, because I'm going to move on to the other, and we'll check tomorrow. Check to see what we got there. So you just plug that into a calculator to get it. Plug in t is equal to 4. Okay? And so we finished the next example, and it seemed pretty well. And then we have this last problem on logarithmic differentiation. So sometimes the properties of logarithms can be used to simplify the process. Now here's one really quick example. If I have something like this, y is equal to ln of x cubed times the quantity, let's just say, who cares? I'm just making this up, over x to the 5th power plus 1, like that, something like that. It actually benefits you to use the logarithm rules, because then you can write this as such. You could write it as y is equal to ln of x cubed plus ln, so it's really the ln of this whole quotient, ln of sine x, and then minus ln of x to the 5th plus 1, and that has to stay, of course, together. But then you would have 3 ln of x plus ln of sine x, and then minus that ln of x to the 5th plus 1. So that when you took the derivative, your derivative is a little easier rather than jumping into a beautiful, I use that facetiously, a beautiful quotient rule. It's on top of it. So logarithm rules are tremendously helpful when you're working with expressions such as logarithms, and you can transform them, but they also have a use when you're working with expressions where the variable is in the base and the exponent at the same time. Okay, so that's what we're going to do here. We're going to find dy dx for this last one. So what we're going to do is we're going to say, all right, well, y is equal to that. So y is equal to, I'm going to leave a little space. I have x to the cosine x here, right? So what I'm going to do is I'm going to take the logarithm, and I typically do not use base 10 logarithms. It's just, I'm much more comfortable using natural logs, and I'm sure many of you will find that one or the other, but we use the natural logs a little more often. So now here's what I have then. I have ln of y. So then with the natural logs, it helps us to get the variable expressions that have x in it down on that baseline in the, quote, numerator, if you will. So we have then cosine x and times ln of x now. All right, so on the next line then, we're going to go ahead and take the derivative of each side, and then we're just going to place the ddx, taking the derivative with respect to x implicitly, so on the left and the right-hand side. And so on the left-hand side, I get 1 over y and dy dx, sorry. So remember, we want to find dy dx, and then is equal to, now I have the product rule on the right-hand side. So I have first, dir second, and I'm going to put parentheses, 1 over x, plus second, ln of x, times the derivative of the first, and that would be negative sign is the derivative of cosine. Okay? So now we want to solve for dy dx, so we're just going to multiply both sides, take the whole enchilada, and we're going to multiply, and we'll do some simplifying as well, but we're going to multiply both sides by y. So we get dy dx then is equal to cosine over x, cosine x over x, and then I'm going to write this as minus instead of plus, because there's a minus sign with the sign. And so I'll write that as sine x. I don't know why I like it that way, but it doesn't matter. It's the commutative property. So I'm going to take all that, and then I'm going to multiply by y, but now I'm going to put the y in there, which is x to the cosine x. And it isn't really the most beautiful expression in the world, but shy of, you could make this one fraction if you wanted to. You could distribute the x to the cosine x, and you could do some things with it, because if you consider you have x to the cosine x and then over 1x, like in the first one, you could really write this as x to the cosine x minus 1. But I'm going to leave it just as it is. Okay, that will finish the lesson.